All right, so today we are going to focus specifically on exponential growth, and we are going to make sure that we can graph exponential growth functions, that we can identify their domain and range, and I will also make sure that you can identify the asymptote as well. And then we also want to be able to solve real-world application problems that use exponential growth. So our exponential growth graphs, we had this yesterday when we were exploring the exponential graphs in general. So we've got a times b raised to the x minus h and then plus k. So if this is exponential growth, the part that makes it exponential growth is the fact that here your b, your base, is going to be greater than 1. So base has to be greater than 1 on exponential growth. A, your constant value, it can't be 0. The reason being is if it were 0, 0 multiplied times anything is 0. That would drop out the exponential part and it would just become a horizontal line. So A can't be 0. Now, here is one of the most important things that people tend to forget about their parent graphs for exponential growth. Regardless of whether b is 2, 3, 4, whatever it is, your y-intercept, which we're going to call that our starting point, this is where you are going to start your graph. The starting point is going to be the y-intercept. And until we start having shifts, that is going to be a y-intercept at 0a. So whatever the a value is, as long as there's no h or k, no shifting, that's going to be the value of your y-intercept. Then asymptotes. Asymptotes are always going to be located wherever the k value is. So k represents your vertical shift up or down, and that is also going to be representing the location of your asymptote. So domain and range, again, I want you to be able to focus on finding the domain and range by looking at the graph. Yes, in this case, there are rules, a pattern that you're going to notice. It's going to be all real numbers greater than k if a is greater than 0. For the range, oops, I'm reading the wrong one. Domain is going to be all reals no matter what, the x values. The range is going to be one of these two. So it's going to have a greater than symbol if a is bigger than 0. It's going to have a less than symbol if a is less than 0. So here's a parent graph, a version of a parent graph. With exponentials, if we change the base, it becomes a new parent graph. But in general, what we are doing here is we have no shifting and no a value. So this is just a straight parent graph where my base is 2. So what I want you to focus on is the fact here that my a value, because there is no a written, that means that a is 1. And that means that that is where my starting point of the graph is going to be. So that means I'm going to start at 0, 1. So 0, 1 is going to be my starting point. Now again, you could make a t-chart for all of these and get the rest of the points. So if I know that my starting point is 0, 1, I can plug in x equals 1, x equals negative 1, x equals negative 2, x equals positive 2. And easily come up with numbers to put in here. So when x is 1, 2 to the first power is 2. So 1, 2. And 2, when I plug 2 in, 2 to the second power is 4. Notice the same pattern that arises. If you know this pattern, it will save you so much time to be able to graph these quickly by hand. So I go 0, 1, and then from there, I go from my origin, right 1 up 2 and right 2 up 4. Over on the left side, when x is negative 1, that gives me 2 to the negative first, which is 1/2. Here, 2 to the negative second, which is 1/4. So negative 2 and my y value is a quarter, -1, my value is 1/2. So your asymptote is going to be where your k is. Here my k is 0. There is no plus or minus anything on the end. So that means my asymptote is y equals 0 or the x-axis. I did not connect that very well. It's hard to do on the tablet here. But there's what our graph should look like. So when we go to do domain, range, and asymptote, make sure, and I wrote this on your notes, make sure that you graph the asymptote. So if it's on top of the axis, that's okay. We're going to graph asymptotes with dashed lines. So there's my asymptote. I'm going to label it. That's y equals 0 is my asymptote. So my domain, my x values, well, x is going on forever this way and forever this way, which is why it says up here that the domain is all real numbers. My range, if I look at my y values are getting closer and closer to 0 over here, but they're never actually getting there. So they're not reaching 0, but they are getting close to it on this side. And then on this side, they're getting bigger and bigger and bigger and bigger. Y is going up to positive infinity. So that means it's going to be all real numbers greater than 0. Or if you're using interval notation, it would be from 0 to infinity with a parenthesis, not a bracket. The asymptote, again, we already said is y equals 0. So state the domain, the range, and the asymptote. Got those all on there. So now let's look at B. -2 times 5 to the x minus 1. Here I've got some changes. So my a here being negative means that it's going to be reflected. So my base here is 5 instead of 2, which is going to change my starting area and how quickly it increases or decreases. So that's just a different parent graph. This -1 means it's going to have a shift down 1. So normally your y-intercept is going to be your a value here. So at 0, -2 is where we would think it would be, but because we have a vertical shift, instead of 0, -2, it's going to start 0, -3. So that's going to be my starting point. Again, you can pick other points for a t-chart if you want to make your t-chart there. So when x is, oops, I wrote x instead of the actual value. When x is 0, y is -3. When x is 1, you can plug it in. That'd be -11. So that's already off the chart. When x is -1, 5 to the -1 is negative, or is 1/5. So that's -2/5 minus 1. So -1 and 2/5 is the value there. And just to do -2 for the heck of it, 5 to the -2 is 1/25, so I've got -2/25 minus 1, so -1 and 2/25. So you can see very small numbers there. So if I plot those, again, 1, -11, 3, 6, 9, it's just barely off the graph, so I'm just going to make it right here below it. -1, -1 and 2/5, so almost a -1.5, so right here. And then the next one, still -1 and 2/25. So my graph, if you continued it, if you looked in your graphing calculator, would look like this. Notice what it's approaching. The k value is my asymptote. So my asymptote goes here at y equals -1. So domain, x values, x going on forever this way, x going on forever this way, so all real numbers. Range. My values are starting here. They're not getting to -1, but they're getting close to it, and it's going to negative infinity. So that's going to be all reals less than -1, or from negative infinity to -1 if you're using the interval notation. The asymptote we already discussed. It's the line y equals -1. So there's my info. All right, I would like for you to try C here. Notice that the -1 here, you're going to have a shift. So go ahead and try to produce C and pause it and then come back to see if you have it right. So first thing I'm going to do here, this A value would typically mean that my starting point would be at 0, 4, but I have a shift here. Because I have a shift, this -1 means I'm shifting right. So if I'm going to shift right 1, that means that becomes 1, 4. So I know that that's going to be a point on my graph. So there's 1, 4. So if I'm starting there, then I'm also going to plug in 0, -1, 2, 3. So I've got 1, 4. When x is 0, 5 to the -1st is 1/5, so that gives me 4/5. When it's -1, that gives me 4 times 5 to the -2nd, so 4 times 1/25, so 4/25, very small. When x is 2, 2 minus 1 is 1, and 4 times 5 is 20. So I'm not even going to bother plugging in 3 because I know it's going to be bigger than 20, which is not going to fit on my graph. So I'm going to plot these 2 points, 0, 4/5, so it's not even to 1, and then 0, 4, or -1, 4/25, which is very, very small here. So there's my points. So my domain is, again, always all reals because it's going on forever on both sides of the x-axis. My y's start at 0 and get bigger, but they do not include 0, so greater than 0. And then my asymptote, which I need to graph with a dashed line, my asymptote here is y equals 0. Or if you wrote x-axis, that would be fine as well. So hopefully you did well on that one and got it correct. If not, we're going to try one more to hopefully see if you know what you're doing. So I've got some shifting here. This -3 means I've got to shift right 3. This +4 means up 4. So my A value here is 1, which means I would start at 0, 1, but because I have a shift right 3 and up 4, that means I'm now going to be starting at the point 3, 5. So I go to 3, 5, and I make my starting point. Again, here I just kind of prefer to make a T-chart. So I've got 3, 5, so I'm going to try 2, 1, 4, 5 possibly. So when I plug in 4, 4 minus 3 is 1. So 2 to the first, 2 plus 4 is 6. So the point 4, 6 is going to be on there. When x is 5, 5 minus 3 is 2. 2 squared is 4, and 4 plus 4 is 8. So the point 5, 8 will also be on there. Then when x is 2, 2 minus 3 is -1. 2 to the -1st is 1/2. So this gives me plus 4 is 4.5. So 2, 4.5. And then when I plug in 1, 1 minus 3 is -2. This gives me 4 1/4. So very small. You can see if you continued it, it gets so close to that line, but it's never going to touch it because that is my asymptote. So I'm going to draw in my asymptote here. You should know its equation because, again, your asymptote is always located at your k value. So k is 4, so y equals 4 is your asymptote. The domain and range, domain is all reals because it's going on forever both ways. The range, my y values start at 4, but not including 4, and they get bigger. So all reals greater than 4. All right, so hopefully between this and the day before working on exponential graphs, you're feeling a little more comfortable with the shape that they are taking. Again, notice that when A is positive, as in these three, it's going up, it's increasing, and when A is negative, we reflect it over the axis and it's going down. All right, now we're going to look at some real-life problems with exponential growth. And this is a general formula for exponential growth. We can model a bunch of different things with this. Most commonly, we use some types of inflation as well as population to use this type of growth. But in this formula, A stands for the initial amount. How many of whatever you're talking about did you start with? T is time. R is the growth rate, but the key is that it's as a decimal. So if it's a percent, you have to convert it to a decimal. We call the base, the 1 plus R, the growth factor, because if the growth factor is 2, we're doubling, and so on and so forth. So the population of a town is modeled by P equals 6,191 times 1.04 to the T, where T is the number of years since 2000. So it wants to know what the population is in 2000. Now, T is the number of years since 2000. So in 2000, it's been 0 years since 2000. So you could certainly plug in 0 for T and solve it. However, 2000 is our starting point, and we're told that A always stands for the initial amount, how many you started with. So really, you can just look here and say, this is my initial amount, and it is 6,191. So 6,191 was the population in the year 2000. What is the rate of population growth? R is the growth rate, and 1 plus R, the entire base, is the growth factor. So here, I see that my 1 plus R is 1.04. So really, this is just an equation. I'm just solving for R. I want to get it by itself, so subtract 1 on both sides. That means R is 0.4. Which means the rate of population growth is 4%. And the more you do of these, the more you'll just be able to look at it and write the answer. Last question, what was the population in 2006? Well, 2006 is 6 years after the year 2000. So all this is asking you to do is plug in 6 for T. You can certainly use your calculator to help you here. I don't know what 1.04 raised to the 6th power is off the top of my head, so I don't expect you to either. But you should be able to press this into your calculator, and hopefully you come up with 7,834 is the population. Example 3, we're talking about tuition at a university. This is something that inflates over time. So here it's giving us the information and wants us to write the model. Now the key is when it says write a model, that means leave time as a variable. This is one of the most commonly missed things on a quiz, on a test, on practice problems. When it says write a model, we want to leave T as a variable even if they tell you what it is. So leave time as a variable, write a model that gives the tuition Y, T years after 2010. So in 2010, the cost was $9,420. So that means that's my initial amount. So I'm going to say Y is the tuition, my initial amount, $9,420, times, it says it's going to rise 4% each year. Well, the next thing I need to put in is 1 plus R. So the growth rate, 4%, is 0.04. So 1 plus 0.04 is 1.04, just like it was in the last problem. Again, leave time as a variable. I know it says during the next 8 years, but when we write a model, we leave that time as a variable. So this is going to be our answer here. The next thing it wants us to do is estimate the cost of tuition in 2017. So that's when T is 7. So now we're plugging in the T value. And that's as simple as punching it into our calculator. Hopefully you get 12,396.08. Please check to make sure you can punch this in, because otherwise you don't know if you can or not if you haven't tried it. So please try it so that if you're having trouble, I can help you with it tomorrow. All right, last one. Compound interest. There's a difference between regular interest and compound interest. Compound interest uses a completely different formula than regular interest or inflation. So whenever it says compounded interest, you're going to use this formula. So here's the formula. We just need to know what they stand for. So A is your total amount, P is the principal, which is another fancy way that in the banking industry they say the initial amount. R is your percentage rate. N is the number of times compounded per year. That means how many times are they figuring the interest. Sometimes it's yearly, monthly, daily. T is time in years. So you deposit $1,500 into an account that pays 6% annual interest. Write an equation and find the balance after 7 years if the interest is compounded, and then it gives you all these different options. So compounded annually means that N is 1 because you're compounding it once a year. Semi-annually means N is 2. Quarterly would mean that N is 4. So we're just going to find out different balances versus for my various times of compounding. So $1,500 is the initial amount for all of them. Then the interest, 6% as a decimal, is 0.06. So I've got 1 plus R is 0.06. divided by N, so in this case N is 1, to the N times T. T is 7 years. So NT in this case is 1 times 7. Down here I'm going to be doing 1 plus 0.06 over 2, because it's semi-annually, to the 2 times 7. Down here 1 plus 0.06 divided by 4 to the 4 times 7. Now, you can press this all in one step. However, very few people actually do it correctly when they do it. So I might suggest actually starting here and doing 0.06 divided by 4, then adding 1, taking that answer and raising it to the 28th power, and then taking that answer times the 1,500. Again, it's up to you, but when there's not a lot of work to show, if you're continuously getting the wrong answer, it's probably because you're not pressing it into the calculator correctly. So I always show a little bit of work. I always do this part first, and in this case, 0.06 divided by 4 gives me 0.015. So I always write out the next step, and again, this is optional, but again, partial credit is always good. So I write this next step out. And then once I get to here, then I punch it into my calculator because I'm pretty confident that I'm not going to press the wrong button here. So I've got $2,275.83 if my interest is compounded quarterly. For semi-annually, again, I'm going to write out my middle step. I do the 0.06 divided by 2, which is 0.03, so 1.03, and this time raised to the 14th power. And that's going to give me $2,268.88. And then finally up here, 1,500, 1.06, and I'm going to raise it to the 7th power. And so now I'll put this into my calculator, and that is going to give me, hopefully, if you've done it correctly, $2,255.45. So you can see the difference in interest here is about $20 over the 7-year period, but we started with a small amount here, $1,500. You can imagine the difference it might make if you started with $100,000, the difference between the different compoundings. So it looks like the more you compound it, the more money you actually get. All right, last question. If your goal is to have $2,500 after 7 years, how much would you have to initially deposit into the account from Part C to meet your goal? So if I want to have $2,500, that means $2,500 is what I want my total to be. So that's what it's equal to. And how much would you have to initially deposit? That's what I don't know. So P is going to be my variable here. It says from the account from Part C. So that means this information here. So I can keep this part the same, the 1.015 to the 28th power. So all I'm doing now is solving for a different variable. So here, order of operations tells me I need to do the exponent first here, and then divide both sides by 1.015 to the 28th power. Again, if you're doing it all in one step, be sure to enclose this in parentheses. If you're doing 1.015 to the 28th power first, and then taking 2,500 divided by that, then that will be okay. The key is not to round here. You can use your second answer button on your calculator to actually get it to display the answer from before. If you don't know how to do that, please ask me. I will be happy to show you. But you should get 1,647.75. The reason I am saying not to round is because your answer will be different. And in some cases, it's going to make a significant difference. Here it might just be, a couple cents, but it will make big differences at some point. All right, that is it for this lesson.